Now we're in lecture 10, mass storage system. What is the mass storage system? Essentially your hard drive, The operating system has to talk to the hard drive. It has to be able to store files on the hard drive, retrieve files from the hard drive.
This is a short PowerPoint, 19 slides.
Yeah, sometimes they're short. All right, so this picture. I don't know if you've ever seen a hard drive like taken out of a computer. It looks something like
Yes,
this.
I have. I've
Yeah.
had fun with that.
It has in the back all these pins,
Not
power
anymore.
connector.
Those are old hard drives.
Is there older? Yeah, they have fewer
Now
pins
they
now.
have SATA port, SATA connectors.
Okay, SATA, yeah.
Yeah.
And then, but anyway, fine. The main point is that this part. They have some kind of, I mean, I'm talking about moving hard drives.
Yeah,
We're not talking about, there are solid state hard drives.
yeah, but yeah.
Okay, so there's a head here that moves across, it's kind of like the head of a record player.
Platter.
This is the platter, it spins and it moves, it twists, and that's how it can get from one track to the next, to the next. There's a difference between this and a record. There's a famous Trivial Pursuit question: how many grooves are there on a normal long playing record? On a vinyl record, how many grooves?
Is it illogical? Is there a reason behind it, or is it just arbitrary?
I'm not giving any hints.
So probably.
What?
64.
More like 64,000.
10 million bajillion. I'm guessing so. 10 million bajillion, exactly.
One on each side. One.
Huh?
There's one groove. It doesn't.
Oh.
It's not separate grooves. It's one groove that's in the spiral.
Oh
It's one groove.
So like, man, how many like
This-
notches, like.
No, but why do I ask that question? Because this is different. They're concentric circles. Here, they're concentric grooves, essentially.
Also,
There, it's not concentric grooves, which means that that's how the head continues to go towards the middle. Starts at the edge, and as it wraps around, it gets to the whole track. But here, it actually has to physically jump. You know, it's on groove one, then groove two. It's not physically a groove, it's flat, but in our conceptions, we can think of it as it's on groove one and then jumps to groove two and it moves. So this head twists and goes to the different tracks.
and also record, the head touches the disc.
Here it doesn't
On the hard
actually
drive,
touch.
If it touches, it's a problem.
If it touches, it breaks it, yeah.
It's a very big problem.
So these are it reads it through magnetism. It doesn't actually touch it. There's also, this picture is a little bit misleading because this looks like there's just one head here. There's actually several, and this disc is actually like pancakes,
Yeah, one for each
like
platter.
this. This is like they spread them out very far. But here it's like they're 10 pancakes, one on top of the other, and there's air between them. And this little thing, this 10 readers, and the readers slide in those gaps. So there's very thin layers, and in between each layer, there's a head reading. So if this head moves forward, all the heads beneath it also move forward. In other words, it's not like different, they don't move independently, all the different readers. The reading heads, they all move to the one track to the next track, they move like. So here you see that like this is like this arm, and this is the reading head, and here's the magnetic reader, and it's all of them are in the same place. Let's say reading track, well, the inner track, let's call it 1, and the next track is 2. So they're all, let's say, over 2. Now, the way we think about it is this is important to know the term. This is a platter. This is a sector. Is that just that one plot? In other words, that's not the same sector. That's a different sector. But and wait, that was the track. This is the track, the whole circle. Like there's the inner track, or what I was calling a groove. We're calling a track, really. There's a track, next track, and next track, and next track, and they're concentric. And each track is cut up into sectors. And then what's a cylinder? A cylinder is an imaginary kind of thing, but it's saying like this: imagine the head is hovering over this track. Well, it's also hovering over this track and this track. So if you imagine all the 10 tracks, one on top of the other, sort of forms a cylinder. So it's actually concentric cylinders. And because it's easier to read, which is easier for me to read? It's easier for me to, if I'm going to read this track and then this track, it's much faster than if I'm going to read this track and then the outer track, because I don't have to move the head. I can just stay at the inner place and read this track and this track. So if I want to read the, if I want to get things done fast, I'd rather have everything stored on the inner track, let's say all the things that are close to each other, if I have a file, I'd ideally like it to all be stored on the inner track, the whole file, part of it's on the inner track, and the rest of it to be on the inner track. I wouldn't want, I mean, I could, in reality, we will do this, but it's unideal to have the file spread out all over the disk. Because I have to move the head all the time back and forth, and that's slow. Anything that's physical is slow, yeah.
Technically, it's better to put on the outside of the hard drive, because when it's spinning, the outside spins
Faster,
faster.
okay.
That's interesting. I have a question. Do we put different data on different platters? Like so-
You mean like different types of data?
Yeah.
No.
No, usually it's
It's
split
all
up,
just the same.
It's all the same.
usually it's the same file split up amongst all the patterns so that it has faster read and write. Because doing all the patterns at the same time as opposed to one by one.
I don't know much about that. That's already hardware. I don't know exactly how fast, if it can read. I don't know if these readers can read simultaneously or not. I would assume not. For our course, we're gonna assume they don't read simultaneously. Maybe in reality they could, but we're gonna assume they don't read simultaneously. Okay, so there's something called seek time. So what is seek? Seek time measures the time it takes for the head assembly on the actuator arm to travel to the track, to the groove of the disk where the data will be read. In other words, if I'm currently on track 1 or 2, and I need to get to track 1, then I have to turn and get there. That's called the seek time. Seek times are not linear compared to the seek distance traveled because of factors of acceleration and deceleration of the actuator arm. In other words, like if you think about it like a car, if I'm driving down the block to my friend's house 2 blocks down, I'll never get up to 50 miles an hour. Because it takes time to accelerate. I'm not going to be, so it's going to be slower to get there. Even if there was no speed limit, I wouldn't be able to get to 50 miles an hour. By the time I get to 50 miles an hour, I'd already passed the stops. So if I have to travel, so therefore it's not linear. In other words, the travel time, the speed, if I have to go a greater distance, proportionally, I'll get there faster than if I go a short distance. There's a certain startup time and slow down time that I always have to pay, like a commission. So commission I always have to pay. Once I pay the commission, as much money as I want to transfer, I can transfer. So, so the seek times are not linear compared to the seek distance. Rotating drive's average seek time is the average of all possible seek times of the drive. What's the average seek time for this drive? Not for a particular event, but for this drive. It's the average seek time of all possible seek times, which technically is the time to do all possible seeks divided by the number of all possible seeks. But in practice, it's determined by statistical methods. I guess by averages or something, by common cases or something. But theoretically,
probably
in other words,
access more often.
right, now I could do a seek from 0 to 8, I could do a seek from 0 to 6, I'm doing 0 to 5. I could do a seek from all the possible seeks. And then I can take the average. We can approximate the average seek time by observing that the average seek time equals half the maximum seek time. Even though it's not really correct. Because the maximum, because of what I said, that it's linear, but it's not linear, this is not correct. The maximum seek time would be the time it takes me to get, let's say, from track 0 to track 20, the furthermost track, let's say, or track 100. That would be the longest seek time. So I say the average will be half of that. Because it's not exactly right, because it's startup and slow down times.
The disk is also round, so you have more information sitting
What?
in a groove farther away.
Yeah, I don't know about that. It could be, not necessarily.
Like it would be spaced out more.
Yeah, it could be. I don't know. I'm not going to answer that question. Could be spaced out.
The circumference is greater at the.
I agree with that, but I don't know if that means that there's more data. Most common disk, like I always wondered about the. Right. Like you think about a tape drive, like an old cassette. If you ever, I have some still. I don't know if you've ever seen them, but you have a cassette. The thing that spins at the same speed. Now, when there's a lot of tape on the spool, it'll be spinning. It'll going past the head reader very fast, right?
Yeah.
And if there's a little, then it spins the same speed. So less tape is going across the head. So
that would be.
how does the head deal with that? You see what I'm saying? The head doesn't change its speed of reading. It's not like it reads fast. I mean, I don't know, there's. Yeah, I imagine that when it wrote it, it also wrote it in a different ratio.
Would write, you're saying if it wrote on the outside is at the same rate that it wrote at the inside, then you'd have, you.
I'm saying if you would like, if you would, what I'm saying is like, it would be interesting to me if you like. If you took the beginning segment, the beginning 30 seconds of your tape and cut it off. And then ran the whole tape and then put it at the end, would it just sound different? Because the record, you know what I'm saying, because the record is a different speed.
The recorder probably does not know the length of it, so that's probably,
And which should logically it should change the speed of it, because because now that same thing that was recorded at a slow rate is now going to be written back at a fast rate.
it was written at the same rate. It was written starting at when it was full. So if it was written when it was
I
full,
understand, as long as you don't mess with it, it should be okay. But I'm saying if you mess with it, you should be able to change it.
then yeah, well, I'm saying that would have to be that way. It would have to be that way.
That's what I'm saying.
So, well, it's,
Most common desktop drives typically being around 9 millis. The average seek time of most desktop drives at the time of the writing of this thing, which is 10 years ago, was 9 milliseconds. But that's pretty slow, yeah. Okay, rotation latency. What, there's something else. So we already talked about the seek time, that's the head moving. But there's also, I need to, let's say I'm reading this track. I don't spin the track. You know, maybe I do spin it, but like, let's not imagine I spin it. Let's imagine that I'm reading this track. Let's imagine everything's very slow. We're in the slowest possible world. First, I read this track. Then I turn the disc and I want to read this track on the other side of the disc. I don't necessarily want to read the track, not the track, the sector. I'm reading this sector, and then I want to read the sector opposite. And then I want to go back and read this sector. Who knows? I don't necessarily want to read the sectors one after the other. So I read this sector and then I read the opposite side sector. So to turn the disc around without moving the head, that's called latency. Rotational latency, sometimes just called latency, is the delay waiting for the rotation of the disc to bring the required sector under the read-write head. It depends on the rotational speed of the disc measured in revolutions per minute RPM. Average latency is half of the maximum latency. The data transfer rate of a drive, also called the throughput, covers both the internal rate, moving the data between the disk surface and the controller on the disk. In other words, when the operating system speaks to a disk, it doesn't speak directly to the disk. There's a little program that it speaks to, and we call it the controller. And that controller is like the agent, the interface, the interfacing agent between me, the operating system, and you, the disk drive. So the controller is like what enables the operating is the interface for the operating system to talk to to get the data, to make a request. The operating system says, I need some data from this disk drive. He talks to the controller, then the controller actually does the work. And that frees up the CPU to, let's say, go do something else. And that also allows the controller to be busy collecting all the data. And then he finally is finished, he indicates it through an interrupt. I've got the data for you. And then the operating system comes, then the CPU comes back and says, oh, you have the data for me? I'll take it. We kind of talked about this in the very beginning of the course. The data transfer rate of a drive covers both the internal rate, which is moving data between the disk surface and the controller, and the external rate, moving the data between the controller on the drive and the host system, the operating system. So like actually guess that. The measurable data transfer rate will be the lowest of the two. Now, it's not the combined, it's the lowest of the two. Now, it's the slowest. Now, the rate is whatever the bottleneck is. Because it could be that I read at this speed to the controller and then I read back. And then I read from the controller to the thing, and it could be the different speeds. So whichever is slower, that's the rate.
it would definitely have to be, like.
It should be combined. What?
They have to be sequential.
It would have to
So
be.
that you're always reading and writing.
No, because we're talking about a rate, and it could be, it's a rate, so it could be, imagine water going through a pipe. So, in other words, you're right, it's reading, and then it's writing, but then it's reading something more, and then it's writing, and then it's passing it on. it's constant, it's a flow. Let's say I want to read the whole disk. So I want to copy one disk to the other disk. So the rate is the rate at which I can get it out and on. So it's this, whichever is the slowest, right? Whichever,
Pipeline.
it's a pipeline, it's water flowing through, there's a I read, it's true, I read and then I send, I read and I send, but there's a constant movement here. And this, so therefore there's a rate.
Yeah, why we're not combining the 2 times? 2 rates?
Because while I'm doing one, I can do the other. I can do them simultaneously. While I'm reading data, let's say, into the controller, I can also get it out of the controller. As the previous data I can get out. If it would be just like a one-time thing, I want to read 1 byte, then you're right, it would be the time it takes to read that 1 byte.
Oh.
And then the byte further. But I'm reading hundreds of bytes, so I can read a byte and then push it out, and then read another byte, and I'm asking like, in an hour, how many bytes can I read? So it's a rate, so it's what slows it down, the slowest of the two. Okay. So average access is very similar to the data, it's very confusing because for me, especially as a teacher, because it's very similar to what we did in architecture. Because we have the same kinds of things,
Absolutely.
same terms. You guys already forgot that other part, so.
Rates.
What?
Well, we also have the.
Latency, we have EAT, effective access rate,
What's here?
access time. Anyway, average access time. Average equals average seek time plus average latency. So in other words, there's 2 things you gotta do to get a piece of data. You gotta get. This is now, this is the rate, this is the transfer rate. We're not talking about transfer rate now. We're going back to the first 2 things we talked about, which was turning the disk. Getting to the right sector and getting to the right track. Right, moving the head to get to the right track and moving the disk, that's called latency, to get to the right sector. Because the head doesn't move, I just have to move the disk around to get the sector under the head. So now we're going back to that thing. So I say like this, the average access time equals the average seek time plus the average latency. So I gotta move the head to the right track, and then I gotta turn the disk to get the sector in the right place. Both of those things have to happen one after the other. Data transfer time. So how long does it take me to transfer, let's say 100 megabytes of data? It equals the average access time plus the amount to transfer divided by the data transfer rate, which the rate we talked about. Now it's 1 million megabytes, and then we can do 1 million megabytes a second, then that's 1 second. Plus the average access time. Except that you could say,
That's included in the.
you could say times the average access time, because for every byte I need to access it. Plus the controller overhead. Okay, this is what we're saying now. Average access time plus the rate. For example, an average seek time of 5 milliseconds. 5 milliseconds. And an average latency of 4.15 milliseconds, 1.6 milliseconds. And a data transfer of 1 gigabyte per second. Oh, gigabit, I wrote a little b, that means gigabit. Because, oh, that's another thing, just like the internet, we measure rates usually in bits per second, not in bytes. Because we want it to flow, it's like how much water, it's a flow, it's not, whatever, we measure in bits, because each bit is a new flow. There's other reasons for it, but let's say a
The
byte,
numbers look bigger,
what?
makes the numbers look
Makes
bigger.
the numbers look big. But it's always measured, when you buy a hard drive, it'll tell you its transfer rate, it's always in bits per second, not in bytes per second. That's the way it's measured. So controller overhead is 0.1 milliseconds. So now to transfer 4 kilobytes block, now on a 7,200 RPM disk, that's gonna be irrelevant information. We don't care how, because we already know the data transfer, like we know the seek time, the data, I don't care how fast it goes. I know, if I already know the rate, I don't care how fast it goes. And I don't know the relationship between that speed, how fast it spins, and the rate. So. What do we get? 5 milliseconds, where's that from? That's the seek time, right? 5 milliseconds plus. Oh, plus the controller overhead, Well, so it's these, the average access time is these two together, 5 + 4. Plus, 1 is the controller overhead is controller overhead, so that's 1. So 5 + 4 + 0.1. And then the transfer time, but in other words, this is like kind of, you can imagine, to get us in the right place. And start going. We always have to pay, we always have to pay that price, to get it, that's our commission, to get in the right place. Now, okay, and then 1 millisecond is the overhead for the controller to like. I don't know, he slows it down, whatever, that's his slowing down. And now, we have the actual transfer, and the transfer time is 4 kilobytes, this is where it gets confusing. 4 kilobytes divided by 1 gigabyte, as we can do 1 gigabyte, we want our time. Gigabit. So, because we can do 1 gigabit per second. So if it's 4, it's not gonna be 4 million, it's gonna be less, like the speed, the bigger the speed, the smaller the time, right? So that's why it's divided by.
First thing I would
The
do is-
speed is vast, the bigger the speed, the smaller the time, so therefore we divide.
first thing
And
I
this is
would
the
do-
amounts that we're gonna divide.
I just changed kilobytes to kilobits to make.
We have to, so let's change let's get them all the same units. So what is this, 4 kilobytes is 2 to the 12th bytes, right? 4 kilobytes, a kilobyte is 2 to the 10th, and 4 is 2 to the second. 2 to the second times 2 to the 10th is 2 to the 12th. So that's 2 to the 12 bytes. Now, how do I get this 27? Well. If it would be 1 gigabyte, it would be 2 to the 30th, right? A gigabyte is 2 to the 30th.
Yeah.
Remember, a megabyte is 2 to the 20th, a kilobyte is 2 to the 10th, you gotta remember that. So a gigabyte is a gigabyte would be 2 to the, but this is not quite that much, it's not quite that fast. It's an eighth of that. So we have to divide it by 8. Well, divided by 8 is dividing it by 2 to the 3rd. So it's just taking away 3 from the 30. So it becomes 2 to the 27th. You understand? 2 to the 27th, this is 2 to the 30th divided by 8. So now we changed the bytes into bits because it's 8 bits to a byte.
Wait, hang on. Isn't 1 kilobit 1 to the 10?
Kilobyte.
Byte or bits?
Well, kilo doesn't matter. The word kilo means
1,000, yeah.
2 to the 10th. If whether it's a bit or a byte. 2 to the 10th, whatever it is. I could say I have 1 kilo, I have 2 to the 10th chairs, I have 2 to the 10th chairs, I have 2 to the 10th bits, 2 to the 10th bytes.
That's actually like
2 to the 10th anything,
Oh, okay, so we're looking at,
kilo chair, I got 2 to the 10th anything. 2 to the 10th, I'd like that 2 to the 10th Dunkin' Donuts,
so
but I don't.
1 gigabit in, wait, so 1 gigabit in bit would be 2 to the 30, but 1 gigabit in bytes is 2 to the 27?
I converted everything to bytes.
Alright.
One
Yeah,
1 gigabyte bit becomes
is 30, but
is 2 to the 27th bytes per second.
Because
Wait, but I mean,
2 to the 27th bytes per second.
according to the definition of giga being 2 to the 30th, then a gigabit is 2 to the 30th bits.
Yes, this is 2 to the 30th bits, this is 2 to the 30th, this is 2 to the, which is equal to 2 to the 27th bytes.
That's okay.
So now everything's in bytes. And now what do I get? I get bytes divided by bytes, the bytes go away. The units go away. And I have, because actually, if you think about it, this is bytes. And this is bytes per second. So the bytes go away, but the seconds, this is 1 over per second, which is 1 over a second. 1 over a second is a second. So we get our seconds back. Actually, it's not seconds, it's milliseconds. Why is it oh no, it's seconds. This number will give us a certain seconds, and then I converted it to milliseconds. Because our transfer rate was in seconds. See, our transfer rate was in 1 per second. This number is in seconds. Somebody can do this in math. You'll get some number,
1 over 2 to the.
but then you have to multiply it by 1,000 to get milliseconds. Somebody do that. What is 2 to the 12th divided by 2 to the 27th?
Is 2 to the 15.
It's 1 over 2 to the 15th. 1 over 2 to the 15th. Oh, our class is over.
Oh,
But anyway, if you do that, you're not gonna get this number. You're gonna not get this number. You're gonna get 3 more zeros in front of that number.
Yeah.
And that's in seconds, but in order to turn to milliseconds, what?
30.305.
Okay, yeah, 305. Okay. You know, what's a digit between friends? Okay, so we'll stop here. And we'll talk about some more stuff.
Also, another interesting thing about hardware is that actually they don't use air inside, they use. They use